It is 2:30 p.m. UTC+1, and that means it's supercharged time. Hi, I'm Surma.
And I'm Matt.
And we are going to do some WebGL. So buckle in. Let's go. All right, time to do some WebGL. I think you have never done live coding like this before.
No, not like this.
You have done it alone, though, and maybe some people who are here today will have seen what you did. You have done.
It's possible.
You have done a GIF decoder in JavaScript, I think.
Mostly.
Quite interesting because if you haven't done it, the GIF format is a bit weird. But today, I was about to say we're going to do something less weird, but then again, we're doing WebGL, which not less weird.
No.
No, not at all. So let's talk about WebGL a bit before we get into coding straight away, because I feel like there's a lot of misconceptions out there about WebGL and OpenGL and how it works and what it does. And I don't know, help me.
So the first thing to realize, something that confuses a lot of people, is that WebGL is OpenGL. The API is basically the same.
Yes.
WebGL 1 is OpenGL ES2, which may not mean anything to you, but like if you find tutorials on the web for how to do OpenGL, pretty much directly applies to WebGL.
Because I think one of the things that I do know is that it is pretty much one-to-one the C API put into the JavaScript world, more or less, which is not necessarily a good thing, because if you're used to web APIs, this is going to be a whole lot different.
So there's a lot of weird stuff. It's stuff that just looks weird because it doesn't look like JavaScript.
Yeah.
The next thing to understand is, so people think of WebGL as a way to do 3D graphics. And that is what a lot of people use it for. But when you're doing 3D graphics with WebGL or OpenGL, you have to do a lot of that work yourself. Really, all that OpenGL does is draw triangles on the screen really fast.
Yeah, because it does it in most of the processing in parallel, right? Graphic cards are basically cards with processors on them that have up to like 10,000, 100,000 cores.
Something 16,000 is
something ridiculously high, and you can run code on them in parallel. So I think we should start by you explaining what you're going to do and how it's actually going to work. But before that, I want to say hi to everyone who's watching. Hi. As always, I'm going to be in the chat. So if at some point you find a bug, you have a question, or don't understand something, you can use the hashtag supercharge on Twitter or use the chat on YouTube on the live stream. And I'll be monitoring that and will throw you like a little curveball every now and then to see if I can trip him up or not. And that's from my side. Let's go.
OK. So what are we going to be doing? So as I said, the WebGL is for drawing triangles. And you can do whatever you like with that. So what we're going to do is we're actually going to do some 2D image processing. We're going to take an image and draw it into a canvas. And we're going to do some manipulation of it, change the brightness, or maybe make it change brightness across the width of the image.
Filter.
We'll think of something. So we're just going to process an image and turn it into something slightly different.
So right now we're just using the normal canvas, but using a WebGL context for that.
Yeah, so it's going to be the same HTML canvas element, but you can access it in a WebGL way, which we'll show in a sec. But yeah, there's the context, the way that you talk to
this piece of screen estate.
Yeah.
Yeah.
So instead of getting a 2D context, we'll get a WebGL context. OK, so I guess we should talk about how WebGL works.
Yeah, because I don't think that's something we can expect everyone to know about. Not everybody has done game development or OpenGL tutorials necessarily. And it is quite a bit different from, I want to say normal APIs, but the APIs usually come across with when doing web development. Yeah.
OK, so on my tablet, I'm going to show you roughly what WebGL does. So with WebGL, you give it a bunch of information which has to include the positions of some points on the screen. So you define some points. Oops. You define some points. You write a small program that you send to the graphics card called a vertex shader. That takes in whatever data that you give it.
I think I was confusing. It's called a shader, but nowadays it is just an arbitrary code program in the graphics card pipeline. It doesn't only do shading, it can do a lot more. But originally, I guess they were used for creating shadows, and that's why they're called shaders. But now they've moved on, evolved into more complex and powerful beasts.
So your vertex shader, which is the first of your 2 WebGL shaders, what that does, it takes some input that you give it. You can give it whatever you like. And it has to spit out numeric data, and it has to spit out the coordinates on screen of a point. So on the tablet here, we've got 3 points. Let's say we have some more. And then what happens is that for every 3 points that WebGL gets, it assembles those into a triangle. So take the first 3 points and make one triangle. Take the next 3 points, make a new triangle.
So what this vertex shader does is convert your arbitrary data, which in the game context would be, I guess, the points of your 3D models that are somewhere in the 3D world, and would convert them to on-screen positions. So in the vertex shader is where usually the whole perspective distortion thing happens, which we're not going to do today because we're doing 2D image processing. OK, continue.
OK, so you run the vertex. Well, your vertex shader runs. It gives you the points. The graphics card goes away and turns those into triangles. It then does rasterization, which is that it takes each triangle and it works out which pixels on the screen intersect with the triangle. So here's my beautiful diagram.
As of now, it was just screen coordinates, which doesn't necessarily correspond to individual pixels. It's just floating point numbers on screen coordinates. And then it figures out for you, if these 3 points form a triangle, which pixels would be affected by that triangle.
Right. And then for every pixel that is part of that triangle, it then runs the second shader called the fragment shader. And this basically, it can have some information that's been passed through from the vertex shader or from elsewhere, but it basically has to output what color is this pixel. So the vertex shader says, where are the corner, where is this point on screen?
Yeah.
And the fragment shader says, what color is this pixel? That's all that they do.
There's a distinction between fragment and pixel, but I don't think it's worth getting into.
Yeah.
I still haven't understood it myself. So let's just say the fragment shader colors pixels, and we can work with that.
In other graphics libraries, like the in DirectX, it is actually called a pixel shader.
Huh.
Instead of
That makes more
shader.
sense, I think. OK, cool.
So that's the basic process. We need to create 2 shaders, a vertex shader, a fragment shader, one which outputs positions, one which outputs colors. And then we need to bundle up some data to pass to the vertex shader so that it knows how to get those positions. And then it should draw our thing on the screen. That's the basic process.
So let's try that, I would say.
OK. So let me we'll come back to that in a sec. So code. So HTML file, it's literally just a body with a script tag to load our script.
Because we don't need much else, do we?
Just going to do everything in JavaScript in this case. So our app.js here. First thing we're going to do is we're going to create a canvas. It's where all the magic starts.
So again, canvas, you probably know it. It's this DOM element that you can get access to with a drawing context and can start drawing on it. But you can also get a different context. So usually you use the 2D context to have line drawings or ellipses, some form of visualization or animation. But you can also get a WebGL context, which turns this context object into this very thin wrapper around the OpenGL API.
Exactly. So here I'm going to get that context. I'm going to put it in a variable called GL, mostly for consistency with everyone else. Historical reasons, that context gets called GL.
That's true. I think every tutorial calls it GL. So
oops, we get a WebGL. Yeah, we get a WebGL context. Then we can do some basic stuff with that. We want to say, hang on. So the WebGL context can draw on just part of the canvas. So one of the first things we're going to do is set the viewport. So we're going to say it goes from 0, 0 to the GL drawing width WebGL drawing height. This is saying I want the WebGL part to output
Yeah.
over the whole canvas. I want to fill the canvas.
So by default, I think the canvas has like 300 by 150 pixels or something like that.
Yeah, we could
Um,
change that, but
We're going to change it later, maybe, but this
Yeah.
basically just ensures that GL knows what size of a canvas we're working on.
yeah. And to make it so that we can actually see where it is, we're going to set a clear color for the canvas, which could be anything. I'm going to make this one sort of orangey. Can't type and think at the same time.
It's an overrated skill for software engineering anyway.
And then we're going to say that the canvas should be cleared. OK, so over here, we can refresh here.
You got an
I
error,
got an
you
error.
got
Oh,
an
right, yeah, OK.
Ah.
So when you clear the canvas, there's multiple things that can be cleared.
Yeah.
Don't worry about that, but we need to specify that we want to clear the color buffer. So we use the color buffer bit.
So one thing that even if you haven't done 3D programming, you might have heard of that you have the buffer for the image that you're rendering, but also a separate depth buffer where you store how far away an object from the camera is, so you know if another object should be painted above it or not be painted at all. So this is something you can clear separately here. We only care about the color buffer bit because
Yeah.
we don't want to do any 3D once again.
There is at least one more other buffer that we haven't mentioned. But like, yeah, as I
There's
say,
buffers.
we're clearing the colors. We're clearing the colors. That's the important
That's
bit.
the one that's being visualized, and we clear it.
OK, so here is our canvas in the
And
corner.
it's orangey,
here.
as you promised. Great stuff.
Awesome, great success. Done. See you next week. OK, so we know that our canvas has been created and that we're working with it live. Brilliant. Not what we're here for, though. So I said that we need to create some shaders. So we're going to take some source code that we write and compile it into a shader. The language that you use to create shaders is GLSL. It's kind of C-like.
Yeah.
It's supposed to look like C, but it does kind of work differently. There's some things that are nice about it, some things that are not nice about it. Some of the nice things, because it's to do with vectors and matrices and things, like working with those is super easy. But it's very unforgiving of syntax.
Yeah. I remember that earlier in the day, it used to be even harder to write shaders because there was no error messaging whatsoever. It would just not work. You would get a black screen, and you would sit there and look for, did I miss a semicolon? Did I mistype a variable name? Nowadays, you do get some error messages to make it a little bit easier to figure out what you did wrong.
Yeah.
And also, because I haven't mentioned it yet, this is not production-ready code.
Oh,
I mean, it's not even. It would probably make sense to, in the end, wrap this up in a custom element. But for now, we're just gonna, because WebGL is quite the complex API, because with being powerful, there also comes a lot of ability to do things wrong, a lot of things to do in general. We're gonna have a bit of setup work, so we thought we would use as little distraction as possible.
yes.
So you're not even putting the shaders in a separate file. You're just gonna inline the code right away because it's just.
Yep,
Yeah.
might as well.
I agree.
Just go straight into a template string. So here I've written the part of my vertex shader, and it's going to set this GL position variable, which is, as we said before, this shader is all about outputting a position. And we're going to make it's a 4D vector. It's like a 4-element array. There's X, Y, Z, and W. W is like magic for perspective stuff, and you don't have to worry about
and
it.
again, we don't do perspective today, so we can just ignore it,
Yeah,
more or less.
it just needs to be 1.
And then it works.
The Z we're going to set to 0 because, again, we have no depth.
If you're curious about the fourth coordinate, look up homogeneous coordinates on Wikipedia. It's
Yeah.
quite the ride.
So we actually have a first example here of something that GLSL is good for, which is that I'm creating a vector 4. I'm going to use a vector 2, which I haven't defined yet, and then just pass in the extra 2 parameters to make it 4 elements long. So here we're going to say that this shader needs an attribute, which is a vec2. That's a 2-element array, basically, that we're going to call position. So this is the data that we're going to pass into the shader, which we'll show how to do later. We're going to take that position, which is going to be a 2D coordinate, and then we're going to expand it using this vec4 constructor into a 4D vector, which is what GL position needs to be. That shader is now done.
So now I just turned the 2-dimensional position into a 4-dimensional vector, so GL is happy. But that's all that's happening, really. There's no arithmetic going on or anything. So
Precisely. our fragment shader, which I'm going to shorten frag shader, the source is similar. It has a main method that's going to get called. Here, the output is a color, which is the variable GL frag color. This is also a vector force, so it's the red, green, blue, and alpha. Unlike when you're doing like CSS colors and things, all of these are floating point variables from 0 to 1. So what color should this one? Let's go for something a bit more purpley. Whatever.
So that basically tells us if any pixel that is covered by our triangle will now get this color assigned.
Exactly.
OK.
And there's just a couple of extra things. Well, one extra thing I have to do here. For some reason, WebGL doesn't like defaults for certain things. So we actually have to say precision IP float. We have to say what precision all of the floating point numbers in the shader are.
Is it ever not high P?
A lot of people use medium P.
I guess the P stands for precision.
Yeah.
I guess it makes it faster?
Yeah, if you use medium P, but less precise.
Well, I mean, we only have so many pixels, right? All right, cool. So
I assume I could have used either.
So now we are basically, we're just getting data in, we're using it as a position straight away. And then we're just saying everything that is covered by triangles is now
purple.
Purple.
Yeah. OK. So that's our source code. Let's make it actually.
I mean, now it's just a string. We need to tell. So the thing is, it's a language, right? And usually you would think a C-like language needs to be compiled.
Yes. So first of all, we need to create some objects on the graphics card. So WebGL has this great love of creating an object on the graphics card and then like making a pointer to it. So
it is a fairly old API.
Yeah. So we create a shader, and we say what type it is. This one is a vertex shader.
As I said, there's two shader types. There's the vertex shader and the fragment shader. I think in newer versions there is the geometry shader, which we're not going to get into today because crazy.
And you in fact have on newer versions of OpenGL, not WebGL, you have the compute shader as well for doing just arbitrary computation. We don't have that.
We don't need that for a little bit of 2D image processing.
No. So we create our shader objects, but these have nothing in there. It's just like
no, the strings are still in JavaScript.
Yeah, it's just a place on the graphics card that we can refer to. It's literally just an ID at this stage.
We have a handle on them, I think it's called. The vert shader and frag shader variables are handles for these two shaders. And now we gotta like push our stuff into there.
Exactly. So we say that for the vert shader handle, we're going to attach the vert shader source, the string with the source. And we're going to do the same for frag shader. So we've attached the source, and now we can compile.
I was about to ask if that was already the compile step, and apparently it's not.
No, it is not. Sorry, not compile source, compile shader. So we're going to compile the vert shader. And GL compile.
So for all the people who've joined us in the meantime, because not everybody can get to a notification that we go live straight away, welcome. This is Supercharged. This is my colleague Matt, and today we're going to do some 2D image processing using WebGL. And what that means is we are getting in the deep end. We are writing shaders and stuff. So far we have set up a little canvas, and we have turned that canvas into a little OpenGL context. And now we can use the OpenGL API from the web, hence why it's called WebGL. And are just about to upload our shaders to the graphics card, compile them, so that we, from now on, can determine how the positions are turned into pixels and how these pixels are then colorized.
Exactly. So we've got our shaders, and they could be used independently. We need to say that they work together in a thing that.
Yeah, because if the one is supposed to pass data from one to the next, because the vertical outputs the position that is turned into triangles that is then used in the fragment shader, they need to be compatible, right?
Yeah. So at the moment, like they don't interact, but later on we will add a way in which they interact, and they will have to be compatible. So we can have we could have hundreds of different shaders and combine them in many different ways. And the way we combine them is in a program. So we create a program. Again, this is just an object on the graphics card, and we get an ID back, a handle to it. Then we attach our shaders. Attach shader. So we use our program, and we use our vert shader. And then same again with the frag shader. So we attach the two shaders to our program. We then link them. So we call link program.
Okay, so we have compiled the shaders. They're now as like programs on the graphics card. Now we link them to one program, telling that program that they need to work together.
Yes. So at this point, it validates that they are compatible and does the plumbing in the graphics card to make it into a single runtime.
Yeah.
Whatever it does. All graphics cards are different, and they tend to be secret exactly what it does. You just see the API.
Black boxes, always good.
Now, as I said, we could have hundreds of shaders. We can also have hundreds of programs linked together, but only one program is used at any given time. So we finally have to say that we're going to use, so use program, and we're going to pass in, the actual program.
Oh, so you can have multiple shaders linked to multiple programs, but you only can have one that the data that you have on the graphics card is being passed into. So you can switch programs, but it would be separate runs of the graphics card, so to speak.
So for more complicated things, you might have different shaders that do all sorts of different things, and during one frame, you might set things up, use one shader, draw that, set things up for another shader, draw that. Use multiple shaders in a frame, multiple programs in a frame, and those programs can be composed of whatever shaders you like. So we've got our shaders set up, linked them into a program. Cool. Now we're ready.
It's good to see that the chat is coming alive with people. Hey, everyone. As always, ask questions. Ask away. I'm going to forward them if appropriate. You can also use the hashtag supercharged on Twitter, which I'm monitoring, if you want to actually understand how we draw things, because we're close to actually having something. I mean, we actually had something on screen already. We had a yellowish rectangle, which is an achievement.
Super exciting.
Let's turn it purple.
OK, so first of all, get the tablet out again.
Literally back to a drawing board.
Oops. Yes, going the wrong way. So let's have, here's one I made earlier, which is a British thing. So Blue Peter reference there for all you UK kids. OK, so we want to draw an image, which is a rectangle. And we can only draw triangles, but luckily we can...
Because that's what OpenGL does best. Draw rectangles and do it in a highly parallelized fashion.
So we have our rectangle.
So that's the fun thing about thinking about OpenGL and WebGL, that we are going to more or less run the shader program that we wrote in parallel in a way that each pixel has its own thread, more or less.
More or less.
So because graphics card have like 16,000 cores, I think you said?
Yeah.
We can do that.
So yeah, each core will probably be used for like 100 pixels or something to make the whole image. Madness. OK, so we split up our rectangle for our image into two triangles. Ingenious.
So the reason why we have to do this is because if there was no triangle, our fragment shader wouldn't get run, and we couldn't change the color of that pixel, which is what we want to do.
Exactly. So we're going to say our vertex shader says where the corners of the triangles are. It works that out, and then we find the pixel colors within that triangle. With no triangle, there's no colors. So we need to say where these corners are to make two triangles on the screen. Now in WebGL, in our shader, when we set those output coordinates, those coordinates for various reasons go from -1 to 1.
Yeah.
So -1 is the left or the bottom of the screen, and 1 is the top and right.
Y goes up, X goes right on the screen. I know this is mirrored for you, so I should be doing this. Y goes up, X goes right, but it goes from -1 is the left border of the screen or the area, and +1 is the right border.
Yeah. I mean,
totally, that's going to be
math. If only we had a way of making diagrams. So let's draw in our axes here. Whoops, it's a little wonky. So our origin here, 0. So this is -1. This pen is set a little thick, but we'll get by.
It's readable.
Yeah.
1 is not a complex number, so it's just... see what I did there? I didn't even intend to do that.
So the coordinates of our triangles, so over here we have, let's label the corners going around like this. I don't know why I did them in this order. It just seemed natural.
It's not even the mathematical order.
No. -1, -1.
So it's an interesting question, like why don't we just use regular JS with Canvas? Because this would be so much faster, or it's going to be so much faster. If we're going to do proper image processing where each pixel will have a considerable amount of math and maybe even dependent on neighboring pixels, that is doable with a normal canvas in JavaScript, but it's going to be slow because you will have to run in a for loop, and you would run this single thread over the entire image. And if you do that on full screen resolution on a Retina display, you're not going to have a good time. With GL, it can do every pixel in a separate thread, and it's going to be snappy fast, arguably 60 FPS. So you can do
I
this
would
effect.
be amazed if it wasn't.
Yeah, I mean, unless you do really, really, I think really blurring filters at high convolution rates would probably not make it, but
yeah,
that's what we're going to do today.
Okay, so we've got our 4 corners. We're going to make them into 3 triangles. The way we're going to do that is we're actually going to make our 2 triangles. There's going to be triangle which is A, B, C, and another one which is A, C, D.
Yep.
So when we have our vertex shader, it takes some positions.
Yeah.
We need to pass in those positions in the correct order.
So we just figured out the letters of the triangles. Now we can replace the letters with the actual coordinates because we also have them in the diagram.
Yeah.
So
let's write in our vertices. Now, when we're passing data to the graphics card, generally you want to use an array buffer. Well, you kind of have to use an array buffer because you have to specify the format of the data so that it fits nicely.
This is a binary transfer. The graphics card works binary, so
yeah. So we're going to create a new float32 array. And we're going to create it from some data, which is our coordinates, which I believe were -1, -1.
That is the
-1,
bottom
1.
Yep.
Yep.
That is
So
the top left.
1, 1.
Top right. So you have our first triangle. These are the 2 dots.
Start from the bottom left again. Then we move to the top right. And then we move to the bottom right.
Interesting question. What is an array buffer? I guess it's something that you don't necessarily know if you haven't gotten in contact with this kind of thing. An array buffer is JavaScript's take on having raw memory, where you actually have a chunk of sequential memory, and you can have arbitrary data in there. And then you need to figure out how do you want to interpret these sequence of bytes. Because you can look them in chunks of 4 and say, these are 32-bit floats, which is what we are doing. You could take the same data and interpret it as integers or something else. And this is the way to make sure that we are actually transferring a certain memory chunk to the graphics card that has the correct format. If we just took an array, it would technically be up to JavaScript to figure out, is this integers, is this floats? And this way we can force a representation, so we can transfer it.
Yep. OK, so we've got our data. Now we need to send it to the graphics card.
Right now it's still only in JavaScript.
So again, we need to create a WebGL object, and this one is going to be the vertex buffer. It's going to be a buffer. Very simple object. So again, we just get an ID back, and now we're going to say what to actually do with that.
So buffer, just again, chunk of memory.
Yes.
This time on the graphics card, though. So now we have a chunk of memory with data in it in JavaScript, a chunk of memory on the graphics card with nothing in it. Guess what we're going to do next?
Well, yeah, almost. First of all, one of the things that's a little weird with WebGL buffers is that you can't just say, create a buffer and then store data in it. That would be mad.
That would be almost simple.
No one expects that. So what instead you have to do is you have named types of buffer. So what we're going to do is we're going to say, we're going to bind, use the bind buffer method to say that the named buffer array buffer points at our vertex buffer.
So you can, so if I understand correctly, you can have as many buffers as you like, but only one of them can take the role of being the array buffer at any point in time. So it's like a slot. You say like, this buffer is now the array buffer, and you do your work. And then for the next draw, you can take that out and take another array buffer. You are now the array buffer.
Exactly. If I wanted to populate 100 buffers, I would have to do this bind buffer 100 times with new buffers.
Yeah, OK.
Yeah, now that we've bound that, we can then send some data. We can use the buffer, buffer data. We can buffer some data. So we say what the target is, and this is that array buffer. So as I say, it is not vertex buffer, it is array buffer.
Sure. So you don't ever reference it by the vertex buffer variable, but just by the buffer that has the current role array buffer.
Yes.
So you have like this level of indirection in there, which is a theme you will find a lot in OpenGL, by the way.
In this case, I could have put the create buffer call right in here because it's literally the only time I use it.
This is nice. This allows us to explain that there is two different concepts, but you know.
OK, so buffer data. So we say what the data is. It is our vertices. And then we say we're going to give a hint to the graphics card about how this is used. And the usage here is GL static draw. There are a bunch of options here, but this one basically says this data doesn't change. So in theory, the graphics card can optimize for this. Some graphics cards do, some don't. Some optimize badly. Some you actually want to use the wrong kind, because otherwise it makes it slow. But we're going to be good citizens and say this is static, because we are never going to change this buffer data. OK. We've got the data. Now we need to hook it up to our shader. Now, in our shader, we've just got this. We've got an attribute, and we've given it a name.
So this is, yeah,
Position.
through this variable, our data will come in.
Yes, this is how it will come into the shader. So in order to say how our data matches up, we need to get an ID for this variable. So we're going to say that the position location, which is a wonderful little linguistic, it's the location in the shader of the position variable.
Oh, so it's like it's in this location in your shader script, so that you can basically then in every run inject a different value.
Exactly. So in the shader, when it compiles, it assigns an index to every variable, so that you can, from outside, say, I'm putting this data into index 0, and it will be whatever variable has index 0. So that you're not referring to the name. So you're not passing strings around all over the place.
Again, a level of indirection.
Yeah.
Cool.
So we get an ID.
Who doesn't
for
love
that
juggling
name.
all of this in your head?
Exactly. So this is, get attrib location. So we're looking inside our program for the attribute called position.
Someone asks, so these C programs, and that person is referring to the shaders, can receive user input somehow by bypassing the browser? No.
No.
But we, as the developer, can set them to values, and that means the run changes. So that is our hook into our statically compiled program to make our scene look different. So one example would be, we could say, this is where our camera is. And then the next run, we don't have to recompile the program, but can just change that bit. And now the camera will be in a different position, and the scene will render differently. So it's basically like, if you want to think about it like C programs, it's like command line flags.
Yeah.
In a way, maybe.
Yeah. Yeah, the WebGL, it has no access to anything that you don't pass through from the JavaScript side.
It's completely isolated unless you, as a developer, give data to it, being the engine.
It would be a pretty serious flaw in the web sandbox if that wasn't the case. OK, so we've got the location. So now we can say that we can point the data correctly. So we say vertex attrib pointer. So we're going to say that the index, which is our position location, we're going to send through, each time it's going to take 2 values. So the size of the data for each run of the shader.
So yeah, it has a chunk of memory. There's some data, but it doesn't know what form the data has. We know it's pairs of 2 because our screen coordinates, and there's 6 in total.
Yeah.
But we need to say that. We need to tell the
Yeah.
engine that. That's how you're supposed to go through this chunk of memory.
Exactly. So on each run of the shader, take 2 values out of the array. The type of those values is float. Normalized is false, and I believe it is spect that just normalized is false. I don't know what that does, to be honest. Stride, this is how far is it from the beginning of one set of data to the beginning of the next set of data. So if you had, say you've got like 10 bytes of information, or 10 floats of information per vertex in your array, but you're only passing 2 through at a time. You might say that the size is 2, but the stride is 10, so that you move 10 forwards to get to the
data
next
is
set.
not relevant, so you can skip over that for every.
Yeah. It sort of, it allows you to skip data. We're going to set that to 0, which means just use the size.
Yeah.
Which is handy. And offset, how far into the data does it, into the array does the data start? It starts at 0. So that tells the shader how to look up the data.
Yeah.
Almost there. We need to enable vertex attrib array. This is position location. So we need to enable this.
So I'm guessing you could have, if you say you can skip it, you can probably say the first 2 bytes of my 10 bytes are a position. The next 2 bytes are the color of this vertex or the normal or whatever, what have you. And so that's why you need to say these. You can enable multiple of these vertex attribute pointers.
Yeah, exactly. So in this case, we've just got one. Is 2 bytes long. So here we say that we want to actually enable this location so that it will, every time we run it, take that data. Because we could say that the shader doesn't care. This particular shader in this run, it doesn't care. We don't actually want it to take that data. Here we do. So we've enabled that. Now we can finally do some drawing.
Ooh, exciting. We're getting
Break out
there.
the champagne. So we call the draw arrays method because we are drawing based on an array, on arrays of data. Our mode is triangles. You can see here from the autocomplete that there's triangle fan, triangle strip, there's point and line.
Oh, OK.
We're doing triangles because it is the most useful thing to do.
Yeah, yes.
So we're going to draw some triangles. We're going to start with triangle 0. And we're going to draw, sorry, it's not triangle 0. We're going to make it from vertices. So we're going to start with vertex 0, and we're going to go, we're going to draw 6
Oh, that's
vertices.
confusing a bit. I mean, you say, I'm drawing triangles, but then you tell the number of vertices instead of the number of triangles.
Exactly.
Because that means, what if I say 7?
Then it will try to read beyond the buffer.
And then
I don't actually know,
everything will explode.
because that doesn't make a triangle.
That's why I would say, I would expect it to be a number of triangles, because then it can't go wrong, unless you go negative or something weird. But
for triangle fan and triangle strip,
they
you
can, yeah,
just
true.
add small numbers.
Either way.
Anyway.
Not today.
So let me just check that I got all the parameters there. Yep, just
Yes,
3. Deep breath. OK. So
The moment of truth is happening.
we set up the canvas. We compiled and linked our shaders. We got some vertex data. We assigned it. We sent the data to the graphics card. We assigned it to a location in the shader. Will it draw? Will it draw?
Let's check our yellow triangle, and it turns purple. First try. I'm legitimately impressed. This should not have worked on first try. That's just like writing regexes that are correct on the first try. So I mean, proof that it's actually the yellow is still behind this, because we have cleared it with the yellow, and drawn 2 purple rectangles on top.
So what we're going to do is I'm going to move one of the corners in a bit so that
so it's
the triangle will be
we
same.
should have like a little yellow.
So yeah, if we move this one, the -1, 1, -1, 1. Let's say make the -0.5 and 5. Oop. There we go. So you can see the corner
Cool.
has moved in, and the orange is still behind it.
I believe you now. All right, so that means we have now reached the point where our entire canvas is, I want to say, under our control. It means for every pixel on that canvas, our fragment shader is going to be called.
Yes.
So let's do something cooler than pink, I guess.
So I'm going to add in one step at a time. Slightly different to what I told you I was going to be doing, so don't freak out. So one of the things you can do is you can calculate information in your vertex shader and send it to the fragment shader.
Ah,
And a cool thing happens, because obviously in your vertex shader, it only runs 3 times per triangle, but your fragment shader gets run hundreds of times, depending on how many pixels there are, is that it will interpolate the values. So if, so let's say that the top corner, let's go back to the diagram here. So let's say that this corner up here, this corner here is red. Let's pick a red. So this corner up here starts red, and this corner down here, oops, is
also red, so nothing changes.
is yellow. Then what will happen is that you will get a gradient. So as it goes from here to here, it will go from red to yellow.
So it will. So we assign data to our vertices, saying this vertex top left has the additional data, the color red. The other one has the color yellow. And for every pixel in between that doesn't actually belong to a vertex, it's going to just interpolate by saying, like, OK, this is like 50% in the middle, so it's going to be 50% red, 50% yellow means some kind of orange.
Yeah.
And so we get a gradient for free.
So yeah, it's not really, so I said colors, but it's just some data. So we already showed that a color is a 4-value array of a vector 4.
Yeah.
So I could say that the vector 4 for the B corner is a color that it represents red, and the one for the A corner is a color that represents yellow. And the individual numbers in those vectors will gradually go from one to the other as it goes.
My explanation was a little bit high level, I admit. I was just saying it's going to mix your colors. It's actually just the numbers, the raw data.
It's one of those things that bears saying twice, just because it's like a lot of
It's very
GL
powerful,
things.
I guess. It's something that can really come into advantage.
Yeah, and a bit mind-bending sometimes. But yeah, so that's what we're going to do. Is I'm going to send through. What I'm actually going to send through is the coordinates. So the coordinate of the corner of each corner, I'm going to send that through from the vertex shader to the fragment shader, so that we have a value which is our actual coordinate within the rectangle.
Oh, OK. So basically, in the coordinate system from -1 to 1, you're going to change that to be...
Yeah, so so I will change that to be from 0 to 1, because we need that later when we're looking at textures.
OK.
But that is, yeah. So first of all, how do we communicate between the shaders? So we have a thing called a varying, which means that it varies over the coordinates. It's going to be, we're going to use a vector 2, and I'm going to call it text coords. This is the coordinates for the texture, as I discussed. And we need to set that same thing up in both shaders, so that they can be linked
And just
together.
by the nature that they have the same name, the GL engine is automatically going to figure out that whatever I put out in the first vertex shader is going to be put into the same variable in the second fragment shader.
Exactly. It will
Cool.
automatically link these things together.
So magic.
So in our vertex shader, we'll set what that is. So the text coords, it's going to be, now there's a bit of magic here. So it's going to be our position, which is already a 2.
So our position is the one that goes from -1 to 1. It's our screen position, right? The thing we drew earlier. -1 to 1, -1 to 1.
So for each coordinate, what we need to do is we need to multiply it by, add 1 to get it from -1 to 1 to be 0 to 2.
Yes.
And then divide by 2 to get it to 0 to 1. There was a lot of
I think
zeros
I believe,
and ones.
I think I believe you. So we shift the entire thing to the right, I'm going to try to make it from the viewer's perspective. So we have here -1, 1. We add 1, so it goes from 0 to 2. We just shifted the entire thing. And then divide by 2.
Yeah,
we'll just
scale it back
0.
down.
Divide by 2 is 0. So
So one of the things you might think you have to do is that, okay, so text coords dot x equals position dot x.
is text
plus
coords something
1.
that is a predefined thing by GL or something, a name that you have chosen?
It's a name that I have chosen.
So we could call it Bibbledy-Booble.
Yep.
Cool.
We're not going to because that seems like a bad variable name.
OK. Well, it was worth a try. I always do that, but you know.
Yeah. So you might think you have to do this. You have to set the x and then the y. But because shaders are designed for doing things with vectors and matrices, you can just do it to the whole vector. We'll have to do that. So what this will do is it will take each element of the position and add 1 to it, and then each element of that vector and divide it by 2. Magic.
That's pretty neat.
Yeah. So now when we look up text coords in our fragment shader, it will have the interpolated value of that.
Cool.
So we can actually use that to get the color.
Oh, so we can just visualize it, basically.
Yeah. So
OK,
here,
go for it.
so like I used like up here, I used our 2D vector to make a vector for.
Yeah, to complete the vector. OK.
We're gonna do the same here. So this is going to be our text.
OK, so let me try to predict this.
Cool.
We have now for each vertex, it's going to output its own position in text coordinate, but instead of using the -1 to 1 coordinate system, it's going to use the 0 to 1 coordinate system.
Correct.
And then these are going to be interpolated for the pixels in between and be used as the red and yellow parts of the color. So that would mean that we go from having blue in the top left corner to white in the bottom right corner, and the other two colors on the other corners I just can't figure out.
Red and green.
Red plus blue. So turquoise and purple.
Well, no, because those are the zeros. So when it's 0 green, oh, plus the blue. Yeah, you're right. You're right.
Ha!
You're right.
Well,
you're almost right. I think you got the corners the wrong way around. Oh no. Oh yeah.
There we are.
I don't know why it took a while to.
Oh, it's.
All blue.
I expected it flipped.
Yes, it is. It is flipped because 0, 0 is now the bottom left corner.
Oh.
So it's going to be white in the
Oh, yeah,
top
right. The coordinate
right
system
corner.
is.
Oh, sorry.
Yeah, I was usually on the web. The coordinate system starts top left.
Yeah.
In GL, it does not. It grows towards top and right.
Yeah.
So
it doesn't help that in our explanation, left and right are backwards, whereas in WebGL, top and bottom are backwards. So when we're explaining it on camera with our hands,
Oh God.
it's usually wrong. That does seem a little wrong. I feel like I've done something wrong, but
Looks good to me.
there's no red or green here.
Why would there be? You have always blue in
Or
there.
sorry, there's no. Does it go from purple to cyan? I'm actually colorblind. This is a
looks
terrible
to me-
demonstration for me.
It looks correct
Okay.
to me. So,
Fair enough.
Yeah. To everyone who's joined late, welcome. Glad you joined anyway, because the more the merrier. We are doing some WebGL, and what we're going to try to do with WebGL is something that has nothing to do with 3D. We're just going to use WebGL as a really, really fast triangle drawing engine and do some image processing. So if you think of any kind of filter you usually apply to images, we're going to do that in real time with WebGL because we
Indeed.
can. Because it's actually quite interesting.
So, we can mess around with colors like that. Let's do something more like what we said we were going to do at the beginning. We're going to use an image.
Ah, so considering we're working in WebGL, that probably means textures.
Exactly. Texture, it's just some data, but it happens that you treat it as an image, and you can put an image in it. So it's an image.
I see a recurring theme. It's just like the graphic cards take some random data, and then you need to teach the graphic card how to interpret that data.
Yeah. So we're going to create an image. This is just standard DOM
I think you want a
shenanigans.
new there.
Oh, yeah.
Now I can. This I actually know. This is JavaScript APIs. I know those.
The source is going to be, I called it image.jpg.
Somebody just said, time to build the game of life in WebGL. I think it has been done where somebody implemented the game of life in just shaders, which makes it really, really fast. It's out there somewhere. It's good fun.
So when our image is loaded and is ready to be used, let's do all of the rest of our stuff.
Oh, so we're not going to do anything until the image loads because we need it to be ready to upload to the credit card. graphics card.
Graphics card. Yeah,
Let's
don't
not
upload anything to your credit card.
No,
it does
we-
have a chip on it, but I don't think it could
It's worth a
hold any
try.
of this.
I mean,
Okay, so obviously in production code, you might be using request animation frame to say when you draw things. I'm just going to say once the image is loaded, we're ready to go. So how do we use the image? We need to create a texture object. So we
so yeah. Basically saying, again, I need a chunk of memory to put image data in instead
Exactly.
of random vertex data that we have used.
couldn't guess. It is create texture,
Ah,
just like we had create
that's pretty
buffer,
simple.
create program, create shader, and create everything else.
That is legitimately called create everything else.
So for our textures, first of all, we need to do the binding.
Mhm.
But there's actually two levels of binding here. So you need to say which unit the texture is going in, because in the shader you can have up to, well, it's graphics card dependent, but let's say you have 8 textures you can refer to in a single shader.
So there is a limit. You just can have a certain number of graphics cards on the graphics card.
Textures on the
Take
graphics card. Sorry, you can have lots of textures on the graphics card.
Okay.
But when you're in a shader, you can only refer to up to a
okay.
smaller
You can only
limit
refer to a limited amount.
in
Okay.
a single run of the shader. So we want to say that we are using active texture is, we're just going to say texture 0.
It's a nice number. I like 0.
Because it's the 0 is the default for when we access the shader
Okay.
texture in the shader. And then we actually need to bind the texture. The name that we're using here, so before we had the name array buffer, this is going to be texture 2D. The thing we're binding is our texture. Then we actually set an image into that. So text image to GL dot text image 2D. So our target, which was texture 2D, as I said.
Yeah.
We are, so we actually want the other autocomplete here. So
I'm really excited
map
to see
level is
that
0. That's
the last parameter of this function, as you can see from the Visual Code autocomplete, is the pixels, which can be an image, but it can also be, it's not the first one, but it can also be a bitmap, an HTML image element, or an HTML video element. Isn't that exciting?
lots of things can be drawn into a canvas, which is awesome. So what I've said is the internal format is RGBA. It's going to have red, green, blue, and alpha. The format of the image that we're getting is RGBA because all image elements, the DOM elements, come through that way. The actual type is, so each of those elements, red, green, blue, alpha, is going to be an unsigned byte in the file. Obviously, we get them as a float.
Yeah.
The shader, and the thing we're actually passing through is our image. Okay.
The thing we loaded at the very top that we waited on onload for. That we're
Yes.
just going to pass that in because I guess that is the very slight additional convenience that WebGL has over OpenGL, where it's like, you know, you're on the web. At the least I can do is help you convert web image formats to OpenGL image formats.
Yes. Now we have to set some parameters on our texture. Basically, the graphics card likes to work with textures that are power of 2 in size, so that they are, say, 512 by 512 and maybe 2048 by 248. Our image is just an arbitrary size, so we have to say how. We have
How to
to
deal with that.
set some parameters that tells it how to deal with it. So we're going to set the texture wrap S. So wrapping can happen horizontally or vertically. For some reason, those coordinates are S and T.
I guess what it is for is that if you in the end you're going to pick pixels from the texture and ask what color is this pixel, what should happen if you actually request a pixel that is outside the image? That is where wrapping comes in. Should it wrap around and you just keep going in circles? Should it just repeat the last pixel at the edge? These are the parameters we are setting here because for some reason it makes OpenGL work with images on arbitrary sizes. I think you said it before, so it is basically a magic incantation to make it work. Don't think about it too much.
You don't have to do this with WebGL 2, but with WebGL 1, you do.
Today I learned.
So we also set what to do if the min filter and mag filter is if we're blowing up the image so that 1 pixel of the texture is going to take up more than 1 pixel of the screen, what to do, and vice versa. If more than 1 pixel of the texture is going to be used
into
in 1 pixel on the screen, what to do. Here we're using nearest neighbor filtering.
Yeah.
Because that's, you know what? Let's use linear, it will look better.
Basically averaging out. If multiple pixels are squished into 1 screen pixel, or the other way around, it's going to interpolate between them.
So we can now access this texture in the shader. We've set it to be texture 0, which is the default one in the shader. We don't actually have to hook up anything there.
Cool.
So here we need a kind of variable that's known as a uniform, which is a thing that is the same for every run.
Yeah. So for all the pixels
it's like a global.
that are running this program in parallel, a uniform is going to have the same value. In contrast to a varying that can vary across parallel running instances of your shader.
Yes.
That's what the two differences are. The name standards are a little bit confusing because a uniform can change between runs. When we draw the next version of our image.
Next time we call draw arrays, we could have set the uniform to something else. So here, the type is a sampler 2D, which is a thing for sampling a texture. Don't worry
Sampling,
about it.
meaning what I said before, asking what is that pixel's color.
Exactly.
That's taking a sample in GL speak.
So we're going to call the texture2D function. We're going to pass it in our sampler to say where we're going to get it from.
Okay.
I'm going to pass in our text coords, our 2D coordinates, to say where in the texture to do the sampling.
So well. As
So
if we
now-
had planned this.
So now our fragment color should be the color of the image for every part of the image.
Hopefully. Let's see how that...
Boom.
It is upside down, but we have a picture. So, I mean, the flipping around, I think, is something we can fix pretty quickly, I would assume.
Yeah, so one of the first things I'm going to do here is I'm just going to quickly magic up some style.
Oh yeah, make it bigger.
So the canvas is going to be, how big shall I make it? I don't know what the aspect ratio is, so we're just going to go for
I think it's 2 by 1.
600. Whatever, I've done something different. Beautiful. And it is vertically flipped because something I did not write down and maybe should have done. So for the web, there is actually an extra feature in WebGL that is not in OpenGL, which says all my textures are back upside down.
Oh, that's convenient.
Because when you get it out of an image element, it is upside down from what it would be in most OpenGL libraries.
Well, we're just going to do it ourselves because, you know, we're writing shaders anyway. Might as well.
Yeah, so in our case, I'm just going to say that in our text chords, I'm going to say that text chords.y equals 1 minus, oops, I can't type.
Yeah, so that's basically what used to be 1 is now 0. What used to be 0 is now 1. It's a flip of the y coordinate, and it should be the right way around. So now suddenly the picture of Australia has become a picture, I don't know, Italy, maybe?
So one of the things you might notice here is that I've made it bigger, but it's now very pixely. I don't know if you can see that on the stream. It's very pixely.
Yeah, I mean, that is, even from a JavaScript side, I know that's because the canvas still only has its default number of pixels, which is 300 by 150. So we should probably increase that as well.
Yeah, so what I'm going to do is I'm going to say the canvas.width can be the image.natural width. So we're going to say whatever the natural width of the image is, so that the number of pixels in our canvas, regardless of how it looks on the screen, number of pixels in our canvas is going to be whatever was in the original image. So if we stretch the canvas around whatever we like, it will always be just as good as the original image. There we go. Much less pixely.
So we're going to use this situation, this moment, to make a very short pause. We're going to try to restart the stream real quick to fix the audio issue that's apparently going on.
Oh dear.
We have been out of sync a little bit. So I'll wait for... Apparently we're already fixed. That was quick. All right, you may continue.
Thank you. Okay. So now that we've got our image going, I guess I could set the... never mind. So now we said image processing, so let's talk about how we might do some processing. One of the things we can do in our fragment shader, we can do a little bit of calculation with this color, perhaps.
So this is where we finally fulfill the title of today's episode, because we're not going to just draw an image, we're going to make some image processing happening. So we're going to take an image, we're going to process it to look differently in some way.
So one of the things we can do is, there are various filters that exist. If you use image editing stuff, you get all sorts of filters. Let's change the warmth of the image. So I'm going to set up a variable. I'm just going to make it a float. I'm going to call it warmth. I'm going to set it. For the moment, I'm just going to pick a value out of thin air. Now this filter, when I saw how this was done, I don't know if this is how it's done in every image app, but it seemed magic.
So warmth filter, you probably know, is usually in this image app you can make a picture look cooler or warmer, which gives it like a blue, light bluish tint or like a nice orange tint. On beach pictures, a warmth filter is always nice.
Yeah. So we're going to, instead of sending this straight to the frag color, I'm going to pull it out into a variable.
All right.
So that I can manipulate it.
You could still manipulate GL frag color, I'm pretty sure. But this is also.
And then what you do is you say that color.r. Oh, so our all of the vectors, so vec2, vec3, vec4, all the vector types, you can refer to them with x, y, z, w if you're talking about them as coordinates, or RGBA if you're talking about them as a color. It's just like an alias. Oh. So here, where I say color.r, I'm saying it's just the first.
Does
STUW
work as well?
No, probably not. Maybe. I think it's just the two. So color.r minus equals warmth. No, sorry, plus equals, because we want positive values to make it feel warmer. And color.b minus equals warmth. Which, if you know what that's doing color-wise, that just seems mad. It's just going to bump up the blueness. When you make it warmer, it's going to bump up the redness and bump down the blueness.
Okay.
And vice versa. Now what will happen here is that potentially our warmth, our color values could go below 0 or above 1, but they'll just be clamped to 0 and 1.
Is it something that WebGL does for us, just for free?
So it will happen in the graphics card when it actually gets sent as a pixel.
Yeah.
It'll be like when it works out what the actual color set from the float value, it will do it then.
Okay.
We can, so it won't happen immediately. So color.r could temporarily be negative.
Which sometimes is what you want if you do some further processing after, and you actually want to be aware of like this overshoot or undershoot, whatever the right term is.
Exactly.
It's because the value's not lost right away, but you can be sure that the stuff on screen is going to be correct data, and this looks much warmer.
Yeah.
Now make it cooler.
Dead simple. Just make that negative.
Much cooler.
So again, you can do things like brightness. There are lots of different ways of doing these filters that are like people have studied the psychology of perception and the physiology of your eyes, and they work out these cool mathematical models. And then other people come along and it's just like, it's approximately
just eyeball it.
Add some numbers. So brightness is the same sort of thing. We're just going to say, well, okay, we're going to do it in a
add to
vector
every
way.
one
So
of them, right?
color.rgb.
Oh, we don't want to add to the opacity.
Yeah, so this is known as swizzling for reasons I'm not actually 100% sure of, where you take a vector and just use a part of it. And we're just going to say add on the brightness.
All right, so we are now going to have a cooler but brighter picture. And it is, in fact, brighter.
Yeah.
Amazing.
And because this is happening in the
We
shader,
just built Photoshop.
it's yeah. I think there's a little way to go before we get there.
Maybe. But, I mean...
But this is the principle for a lot of these filters.
And the thing is, we could actually animate these parameters, and it would run at 60 FPS. And I'm willing to bet that it wouldn't be as smooth if you use JavaScript Canvas. If you had to do these operations on every pixel, like add some values to the RG and B value, it would A, be painful, and B, be rather slow. So whenever you want to do like per pixel animations, WebGL is the way to go. I think we're pretty much on time now, so I'm really happy that we just were able to show the actual processing bit to happen. As always, I'm going to ask you to give me the code afterwards so I can put it up on our GitHub repository, which is in a new location, actually. It's now in the Google Chrome Labs organization. It's the UI element samples. The code's going to be in there. We're going to add some comments. So you can play around. You can implement your own processing. You can switch the R and the B around to make the red part be the blue part and the blue part be the red part and destroy your image. Why wouldn't you? Thanks, everyone, for watching. Great to see, again, that there's always people showing up in the chat and asking questions and being involved in what we do. Thank you very much for doing this.
No worries. Thank you.
Lots learned. And I'll see you all next time around. Bye.